The MD5 message digest algorithm is a widely used cryptographic hash function producing a 128-bit hash value, typically expressed in text format as a 32-digit hexadecimal number. MD5 has been utilized in a wide variety of cryptographic applications, and is also commonly used to verify data integrity. MD5 was designed by Ron Rivest in 1991 to replace an earlier hash function, MD4. The source code in RFC 1321 contains a by attribution RSA license. In 1996 a flaw was found in the design of MD5. While it was not deemed a fatal weakness at the time, cryptographers began recommending the use of other algorithms, such as SHA-1 which has since been found to be vulnerable as well. In 2004 it was shown that MD5 is not collision resistant. As such, MD5 is not suitable for applications like SSL certificates or digital signatures that rely on this property for digital security. Also in 2004 more serious flaws were discovered in MD5, making further use of the algorithm for security purposes questionable. Specifically, a group of researchers described how to create a pair of files that share the same MD5 checksum. Further advances were made in breaking MD5 in 2005, 2006, and 2007. In December 2008, a group of researchers used this technique to fake SSL certificate validity, and CMU Software Engineering Institute now says that MD5 should be considered cryptographically broken and unsuitable for further use, and most U.S. government applications now require the SHA-2 family of hash functions. In 2012, the Flame malware exploited the weaknesses in MD5 to fake a Microsoft digital signature. History and cryptanalysis. MD5 is one in a series of message digest algorithms designed by Professor Ronald Rivest of MIT. When analytic work indicated that MD5's predecessor MD4 was likely to be insecure, MD5 was designed in 1991 to be a secure replacement. In 1993, Denbour and Bosseliers gave an early, although limited, result of finding a pseudo-collision of the MD5 compression function. That is, two different initialization vectors which produce an identical digest. In 1996, Dobbertin announced a collision of the compression function of MD5. While this was not an attack on the full MD5 hash function, it was close enough for cryptographers to recommend switching to a replacement, such as SHA-1 or RIPEND160. The size of the hash value is small enough to contemplate a birthday attack. Md5 CRK was a distributed project started in March 2004 with the aim of demonstrating that Md5 is practically insecure by finding a collision using a birthday attack. Md5 CRK ended shortly after August 17, 2004, when collisions for the full Md5 were announced by Xiaoran Wang, Deng Guofeng, Zhu Li, and Hongbo Yu. Their analytical attack was reported to take only 1 hour on an IBM P690 cluster. On March 1, 2005, Arjun Lenstra, Xiaoran Wang, and Ben de Weger demonstrated construction of two X509 certificates with different public keys and the same MD5 hash value, a demonstrably practical collision. The construction included private keys for both public keys. A few days later, Plastimil Clymer described an improved algorithm, able to construct MD5 collisions in a few hours on a single notebook computer. On March 18, 2006, Clymer published an algorithm that can find a collision within 1 minute on a single notebook computer, using a method he calls tunneling. Various MD5-related RFC errata have been published. In 2009, the United States Cyber Command used an MD5 hash value of their mission statement as a part of their official emblem. On December 24, 2010, Tao Xi and Deng Guofeng announced the first published single-block MD5 collision. Previous collision discoveries relied on multi-block attacks. For security reasons, Xi and Feng did not disclose the new attack method. They have issued a challenge to the cryptographic community, offering a $10,000 reward to the first finder of a different 64-byte collision before January 1, 2013. Mark Stevens responded to the challenge and published colliding single-block messages as well as the construction algorithm and sources. In 2011, an informational RFC 6151 was approved to update the security considerations in Md5 and HMAC Md5. Security. The security of the Md5 hash function is severely compromised. A collision attack exists that can find collisions within seconds on a computer with a 2.6 GHz Pentium 4 processor. Further, there is also a chosen prefix collision attack that can produce a collision for two inputs with specified prefixes within hours, using off-the-shelf computing hardware. The ability to find collisions has been greatly aided by the use of off-the-shelf GPUs. On an NVIDIA GeForce 8400GS graphics processor, 18 million hashes per second can be computed. An NVIDIA GeForce 8800 Ultra can calculate more than 200 million hashes per second. These hash and collision attacks have been demonstrated in the public in various situations, including colliding document files and digital certificates. Collision vulnerabilities. In 1996, collisions were found in the compression function of Md5, and Hans Dobertin wrote in the RSA Laboratories technical newsletter, "The presented attack does not yet threaten practical applications of Md5, but it comes rather close. In the future Md5 should no longer be implemented where a collision-resistant hash function is required." In 2005, researchers were able to create pairs of PostScript documents and X509 certificates with the same hash. Later that year, Md5's designer Ron Rivest wrote, "Md5 and SHA-1 are both clearly broken." On December 30, 2008, a group of researchers announced at the 25th Chaos Communication Congress how they had used Md5 collisions to create an intermediate certificate authority certificate which appeared to be legitimate when checked via its Md5 hash. The researchers used a cluster of Sony PlayStation 3 units at the EPFL in Lausanne, Switzerland to change a normal SSL certificate issued by Rapid SSL into a working CA certificate for that issuer, which could then be used to create other certificates that would appear to be legitimate and issued by Rapid SSL. VeriSign, the issuers of Rapid SSL certificates, said they stopped issuing new certificates using Md5 as their checksum algorithm for Rapid SSL once the vulnerability was announced. Although VeriSign declined to revoke existing certificates signed using Md5, their response was considered adequate by the authors of the exploit. Bruce Schneier wrote of the attack that, "We already knew that Md5 is a broken hash function, and that no one should be using Md5 anymore." The SSL researchers wrote, "Our desired impact is that certification authorities will stop using Md5 in issuing new certificates. We also hope that use of Md5 in other applications will be reconsidered as well." In 2012, according to Microsoft, the authors of the Flame malware used an Md5 collision to forge a Windows Code signing certificate. Md5 uses the Merkle-Euro-Damgi NRD construction, so if two prefixes with the same hash can be constructed, a common suffix can be added to both to make the collision more likely to be accepted as valid data by the application using it. Furthermore, current collision finding techniques allow to specify an arbitrary prefix. An attacker can create two colliding files that both begin with the same content. All the attacker needs to generate two colliding files is a template file with a 128-byte block of data, aligned on a 64-byte boundary that can be changed freely by the collision-finding algorithm. An example Md5 collision, with the two messages differing in 6 bits, is D131DD2C5E693D9A06985946784444583 55AD34609F4B30283E4888325714158F7CDC99F D91DBDF280373C5B, D8823E3156348F5B6DACD436C919C6DD53E2B487 DA03FD02396306D248 GDAO, E99F3342OF577E8SAFE54B67080A80D1E. C69821BCB6A8839396F9652B6FF72A70. D131DD02C5E6E4693D9A0698595C2FCAB507124678400485FB7F89. 55AD3406098F41515A0851258F7CDC99FD91. DBD72803733C5B, D8823E3156348F5BE6DACD436C919C6DD53E23487 DA03FD023963006D248 CDAO, E99F3342OF577E8SAFE54B6708028OD1E. C69821BCB6A8839396F965 AB6FF72A70. Both produce the MD5 hash 79,054,025,255 FB1A26E4BC422E54EB4. The difference between the two samples is the leading bit in each nibble has been flipped. For example, the 20th byte in the top sample, 0x87, is 10,111 in binary. The leading bit in the byte is flipped to make 0000111, which is 0x07 as shown in the lower sample. Later it was also found to be possible to construct collisions between two files with separately chosen prefixes. This technique was used in the creation of the Rogue CA certificate in 2008. Primage vulnerability. In April 2009, a primage attack against Md5 was published that breaks Md5's primage resistance. This attack is only theoretical, with a computational complexity of 2123.4 for full primage. Other vulnerabilities. A number of projects have published Md5 rainbow tables online, which can be used to reverse many Md5 hashes into strings that collide with the original input, usually for the purposes of password cracking. The use of Md5 in some websites' URLs means that search engines such as Google can also sometimes function as a limited tool for reverse lookup of Md5 hashes. Both these techniques are rendered ineffective by the use of a sufficiently long salt. Applications. Md5 digests have been widely used in the software world to provide some assurance that a transferred file has arrived intact. For example, file servers often provide a pre-computed Md5 checksum for the files, so that a user can compare the checksum of the downloaded file to it. Most Unix-based operating systems include Md5 sum utilities in their distribution packages. Windows users may install a Microsoft utility, or use third-party applications. Android ROMs also utilize this type of checksum. However, now that it is easy to generate Md5 collisions, it is possible for the person who created the file to create a second file with the same checksum, so this technique cannot protect against some forms of malicious tampering. Also, in some cases, the checksum cannot be trusted, in which case Md5 can only provide error-checking functionality. It will recognize a corrupt or incomplete download, which becomes more likely when downloading larger files. Md5 can be used to store a one-way hash of a password, often with key stretching. Along with other hash functions, it is also used in the field of electronic discovery, in order to provide a unique identifier for each document that is exchanged during the legal discovery process. This method can be used to replace the bait stamp numbering system that has been used for decades during the exchange of paper documents. Algorithm. Md5 processes a variable-length message into a fixed-length output of 128 bits. The input message is broken up into chunks of 512-bit blocks. The message is padded so that its length is divisible by 512. The padding works as follows. First, a single bit, 1, is appended to the end of the message. This is followed by as many zeros as are required to bring the length of the message up to 64 bits fewer than a multiple of 512. The remaining bits are filled up with 64 bits representing the length of the original message, modulo 264. The main MD5 algorithm operates on a 128-bit state, divided into 4 32-bit words, denoted A, B, C, and D. These are initialized to certain fixed constants. The main algorithm then uses each 512-bit message block in turn to modify the state. The processing of a message block consists of 4 similar stages, termed rounds. Each round is composed of 16 similar operations based on a nonlinear function f, modular addition, and left rotation. Figure 1 illustrates one operation within a round. There are 4 possible functions f. A different one is used in each round. Denote the XOR, and, OR and NOT operations respectively. Pseudocode, the MD5 hash is calculated according to this algorithm. All values are in little endian. Note, all variables are unsigned 32-bit and wrap modulo 232 when calculating, var int, 64, s, k. S specifies the per round shift amounts, s, 0 15, equals 7, 12, 17, 22, 7, 12, 17, 22, 7, 12, 17, 22, 7, 12, 17, 22, s, 1631, equals 5, 9, 14, 20, 5, 9, 14, 20, 5, 9, 14, 20, 5, 9, 14, 20, s, 3247, equals 4, 11, 16, 23, 4, 11, 16, 23, 4, 11, 16, 23, 4, 11, 16, 23, s, 4863, equals 6, 10, 15, 21, 6, 10, 15, 21, 6, 10, 15, 21, 6, 10, 15, 21. Use binary integer part of the signs of integers as constants, for I from 0 to 63, k, I, equals floor, abs, sin, I plus 1 a, n for, or just use the following table, k, 03, equals 0xd76 or 478, 0x8c7b756, 0x242070db, 0xe1bdcee, k, 47, equals 0xf57co-faf, 0x4787c62a, 0za83046113, 0xfd469501, k, 811, equals 0x698098d8, 0x8b44f7r, 0xFFFF5bb1, 0x895cd7b, k, 1215, equals 0x6b901122, 0xFD987193, 0za679438e, 0x49b40821, k, 1619, equals 0xF61e2562, 0. XCO40B340, 0x265E5A51, 0x9B6C7 or, k, 2023, equals 0xD62F105D, 0x02441453, 0xD8A1E681, 0xC7D3FBC8, k, 2427, equals 0x21E1CDE6, 0xC33707D6, 0xF4D50D87, 0x455. A14 ed. K. 2831, equals 0xa9E3E905, 0xFCEFA3F8, 0x676F02D9, 0x8D2A4C8A, K. 3235, equals 0xFFFA3942, 0x8771F681, 0x6D9D6122, 0xFDE5380C, K. 3639 equals 0 ZA4 BY 44, 0x4 BF 9, 0. XF6 BB4 B60, 0 XBIB 70, K, 4043, equals 0x289 B7x6, 0 XA127 FAR, 0 XD4 F3085, 0 XO4881 D05, K, 4447, equals 0 XD9 D4 D039, 0 XC6 DB99E5, 0 X1 FAR 27 CF8, 0 XC4 AC 5665, K, 4851, equals 0 XF4 292244. 0 X432 AF97, 0 ZORB 9423A7, 0 XFC 93A039, K, 5255, equals 0 X655 B59C3, 0 X8 FOCCC92, 0 XFFEFF47D, 0 X85845DD1, K, 5659, equals 0 X6 FAR87E4F, 0 XFE2SE6EO, 0 ZA30143114, 0 X4E0811. A1, K, 6063, equals 0 XF7537E82, 0 XBD3AF235, 0 X2AD7D2BB, 0 ZB86D391. Initialize variables, varint AO, equals 0 X67452301A, varint BO, equals 0 XCTAB89B, varint CO, equals 0 X98BADCFEC, varint DO, equals 0 X10325476D. Pre-processing, adding a single 1-bit, append 1 bit to message, /notice, the input bytes are considered as bit strings, where the first bit is the most significant bit of the byte. Pre-processing, padding with zeros, append 0 bit until message length in bits are per mil 448, append original length in bits mod to message. Process the message in successive 512-bit chunks. For each 512-bit chunk of message, break chunk into 16 32-bit words M, J, 0 per mil currency J A per mil 15 currency. Initialize hash value for this chunk, varint A, equals AO, varint B, equals BO, varint C, equals CO, varint D, equals DO. Main loop, for I from 0 to 63, if 0 per mil currency IA per mil 15 currency then, F, equals OR D, G, equals I, else if 16A. Per mil currency IA per mil 31 currency, F, equals OR C, G, equals mod 16, else if 32 a per mil currency IA per mil 47 currency, F, equals B ZOR C ZOR D, G, equals mod 16, else if 48 a per mil currency IA per mil 63 currency, F, equals C ZOR, G, equals mod 16, D temp, equals D, D, equals C, C, equals B, B, equals B plus left rotate A plus F plus K, I, plus M, G, S, I, A, equals D temp, end for, add this chunks hash to result so far. AO, equals AO plus A, BO, equals BO plus B, CO, equals CO plus C, DO, equals DO plus D, end for. Varchar digest, 16, equals AO append BO append CO append DO. Outputs is in little endian. Left rotate function definition, left rotate, return binary OR. Note, instead of the formulation from the original RFC 1321 shown, the following may be used for improved efficiency. 0 per mil currency IA per mil 15 currency, F equals D ZOR, 16 a per mil currency IA per mil 31 currency, F equals C ZOR. MD5 hashes. The 128-bit MD5 hashes are typically represented as a sequence of 32 hexadecimal digits. The following demonstrates a 43-byte ASCII input and the corresponding MD5 hash. MD5, the quick brown fox jumps over the lazy dog equals, 9E1079D372BB6826BD81D3542A419D6. Even a small change in the message will result in a mostly different hash, due to the avalanche effect. For example, adding a period to the end of the sentence. MD5, the quick brown fox jumps over the lazy dog. Equals, E4D909C290DOFB1 CAO68FFADDF22CBDO. The hash of the zero-length string is MD5, equals, D41D8CD98FOOB204E9800998ECF8427E. The Md5 algorithm is specified for messages consisting of any number of bits. It is not limited to multiples of 8-bit as shown in the examples above. Some Md5 implementations such as Md5 Sum might be limited to octets, or they might not support streaming for messages of an initially undetermined length. See also, comparison of cryptographic hash functions, hash clash, Md5 deep, Md5 Sum, Md6, notes. References, Burson, Thomas. A Differential Cryptanalysis Mod 232 with applications to Md5. Eurocrypt. PPA 71 Euro 80. ISBN A3-540-56413-6 Bert den Boer. Antoon Bosseliers. Collisions for the compression function of Md5. Eurocrypt. Berlin. London, Springer PPA 293 Euro 304. ISBN A3-540-57600-2 Hans Dobbertin, Cryptanalysis of Md5 Compress. Announcement on Internet, May 1996. Site Serex. Site Asirist Pseudocode. Retrieved August 9, 2010. Dobbertin, Hans. The status of Md5 after a recent attack. CryptoBytes Tour, Xiaoran Wang. Hongbo. How to break Md5 and other hash functions. Eurocrypt. ISBN A3-540-25910-4. External links, W3C recommendation on Md5.